welcome again in our laboratory. From the previous video, we talked about the fundamentals of spectrophotometry and applications of spectrophotometry. But for this video, we will be talking about atomic spectroscopy. Before that, or before proceeding with the final discussion, let me present to you our learning objectives and our conceptual framework. And now, let's start the discussion.
Good morning everyone, it's me Christine Aloy and my topic is all about Introduction to Atomic Spectroscopy. Atomic spectroscopy is the determination of elemental composition by its electromagnetic composition by its electromagnetic or mass spectrum. The science of atomic spectroscopy has yielded three techniques for analytical use. We have the atomic absorption, atomic emission, and atomic fluorescence. The process of excitation and decay to the ground state involved in all three fields of atomic spectroscopy. Either the energy emitted in the decay process is measured and used for analytical purposes. So if the light, just the right wavelength on a free ground state atom, the atom may absorb the light as it enters an excited state in a process known as atomic absorption. This process illustrated on the right. In atomic emission, a sample is subjected to a high energy thermal environment in order to produce excited state atoms capable of emitting light. The energy source can be an electrical arc, a flame, or more recently, a plasma. The emission spectrum of an element exposed to such an energy source of a collection of the allowable emission wavelengths. So atomic absorption measures the amount of light at the resonant wavelength which is absorbed as it passes through a cloud of atoms. As the number of atoms in the light increases, the amount of light absorbed increases in a predictable way. So atomic fluorescence, this technique incorporates aspects of both atomic absorption and atomic emission because ground state created in a flame are excited by focusing a beam of light into the atomic vapor. So why is it atomic spectroscopy is very important? So because atomic spectroscopy plays a major role as the basis of a wide range of analytical techniques that contribute data on elemental concentration and isotope ratios.
Good day everyone, my name is Michael Martinez and today we will going to discuss about the application of atomic spectroscopy and the instrument used in atomic spectroscopy. Atomic absorption or atomic emission spectrometer have been used in many different industrial, environmental, pharmaceutical, petrochemical, nuclear energy, and food testing academic settings. For example, a medical laboratory could detect the type and amount of toxic metals that could be present in patient urine or blood. In environmental science, could monitor metal pollutant in soil and water. The pharmaceutical industry uses these machines to determine if a metal catalyst after a drug has been purified. And lastly, the mining industry would utilize these devices to detect the quantity and presence of precious metals like gold or silver. In atomic spectroscopy, we have what we call this instrument atomic absorption spectrometer. It is used to detect elements, either liquid or solid samples, through the application of characteristic wavelengths of electromagnetic radiation from the light source. Individual elements will absorb wavelength differently, and these absorbance are measured against standards. In effect, atomic absorption spectrometry advantage of the different radiation wavelength that are absorbed by different atoms. As electrons return to their original energy states, they emit energy in the form of light. This light has a wavelength that is characteristic of the element. Depending on the light wavelength and its intensity, specific element can be detected and their concentration measured.
Now let's proceed with atomic absorption and atomic emission spectroscopy. All atomic absorption instruments are capable of measuring both atomic absorption and atomic emission. It is important for the operator to understand the processes that occur in each technique. Every element has a specific number of electrons associated with its nucleus. The normal and most stable orbital configuration of an atom is known as the ground state. If energy is applied to an atom, the energy will be absorbed and an outer electron will be promoted to a less stable configuration known as the excited state. Since the state is unstable, the atom will immediately return to the ground state, releasing light energy. The process of atomic absorption is illustrated in this figure. The ground state atom absorbs the light energy of a specific wavelength as it enters the excited state. As the number of atoms in the light path increases, the amount of light absorbed also increases. By measuring the amount of light absorbed, a quantitative determination of the amount of analyte can be made. The use of special light sources and careful selection of wavelengths allow the specific determination of individual elements. In atomic emission, the processes of excitation and decay shown in these figures are both involved. The sample is subjected a high-energy thermal environment in order to promote excited state atoms. The environment can be provided by a flame or more recently a plasma. However, since the excited state is unstable, the atoms spontaneously return to the ground state and emit light. The emission wavelengths called emission lines because of the discrete nature of the emitted wavelengths. The intensity at an emission line will increase as the number of excited atoms of the elements increases. There are some differences between atomic emission and atomic absorption. Using atomic emission, the flame serves as dual purpose. It converts the sample aerosol into an atomic vapor and then thermally elevates the atoms to an excited state. When these atoms return to the ground state, they emit light which is detected by the instrument. The intensity of light emitted is related to the concentration of the element of interest in solution. In atomic absorption, the only function of the flame is to convert the sample aerosol into atomic vapor, which can then absorb light from the primary light source, either halo cathode lamp or electrodeless discharge lamp.